So, let us get started with an overview of the basics of random processes, because we will have to deal with these concepts in this course, right. So, it is not too difficult, it will require a background in basic probability. So, I urge you to study the basics of probability through other courses in NPTEL or otherwise, and ramp up on this concept, because if I spend my lectures on probability, we can spend a semester or probably 3 semesters on this course, but I will give you the basics of random signals. A random process x of t, which could be possibly continuous or discrete, is a family of functions that are possibly real or complex, perhaps scalar or vector, defined on a probability space. So, there is a very clear axiomatic definition of what a probability space is, and at specified times T1, T2, so on, the samples x of T1, x of T2 dot dot are essentially random variables. Random variables, random vectors. So, given the probability space omega, the field and the measure x of t comma zeta belonging to the field. So, given the tuple which is omega, the field f and the probability measure p, x of t comma zeta is a function that belongs to this field, for a fixed t on the real line minus infinity less than t less than infinity. So, if you fixed t, then basically this becomes a random variable and that belongs to this field, else it is just an ordinary function. So, when zeta is fixed, x of t zeta is an ordinary time function when t is fixed, x t zeta becomes a random variable. That is, given the 3 tuple omega, the Borel field f and the probability measure p, x of t comma zeta belongs to the field for a fixed t on the real line, which is from minus infinity to infinity, and when zeta is fixed, x of t comma zeta is an ordinary time function, and when t is fixed, x of t comma zeta becomes a random variable. So, given, if you think about waveforms, right, I choose perhaps zeta equals say 0.1, I get one waveform, 0.1 comma t. If I choose say zeta is say 0.5, I may get another random waveform. So, depending upon these parameters zeta, I may get different time functions. So, this is the idea, but if I fix a particular time, say t equals t dash, a particular time is fixed, right, then these points, they are random variables, right, and that distinction is very important. I mean, when we just learn probability, we just look into random variables and then we look at some properties associated with these random variables, but with signals we have to think about random processes, which means given a value that it takes, the random variable takes, right. I mean, you basically, depending on the parameter, you have basically a time function. So, imagine a process which is a sine omega t plus phi. Suppose I say that phi is uniformly distributed between 0 and 2 pi, right. Now, if you plug in phi equals 0 here, you have a sine omega t, you plug in phi equals say pi by 2, you get basically a cosine, right, you get different waveforms, but you fix a particular value of time and observe, this basically are random variables. Okay. So, I think it is a very important notion, and often in signals can be thought about as random signals, because there may be parameterization in terms of a random phase or a random amplitude, possibly a random frequency, we do not know, right. So, these things could be basically random variables, and then once you specify those parameters zeta, then basically you have a function of time, right. So, basically a random process has two parameters zeta and t, and once we specify the random process, we are interested in some of the statistics of these random processes. So, we will just basically define some of these properties and then more rigorously get into the statistical specification of a random sequence. Okay. So, mean and correlations. The mean of a random process is denoted as expectation of x of t and can be a function of the time index. So, mu x of t is basically defined as expectation of x of t. So, I think one of the questions that may come to your mind naturally is, how are you computing this expectation, right? I have this waveform in time, am I taking all the samples across time and taking an empirical average over this, or I take a collection of all these waveforms and then I average over the distribution of the underlying random variable or vector, right. So, these are two questions that naturally come into your mind, right. How are you calculating this average, right? Is it just a normal time average that you think about, or is it the statistical expectation, right. So, depending upon that, there is a time averaged mean and a statistical mean. So, get this in your mind very carefully. I mean, you will not perhaps have to deal with this when you think about just the normal statistical mean, right. I give you some distribution, Gaussian distribution, I ask you to compute its mean, or uniform distribution, compute its mean. You can compute it, you do not have a big problem in doing it. Here now you have to imagine you have a collection of all these waveforms. Now, do you pick one waveform that you get from this collection of waveforms, just do a time average on that, or you collect all the waveforms and take the statistical average over the underlying distribution of the random variables and then get what this average waveform is, right. These are two different notions which have to be crystal clear in your mind. So, how you take the averages are sort of the details here. And mean can be a function of the time index, as one can expect, right. The mean itself can be a function of time. Now, similarly to what we have considered for the mean, there is something called the autocorrelation function, and the autocorrelation function is given by Rxx of T1 comma T2, that is parameterized at two different times, T1 and T2, and this is basically the expectation of x of T1 with x conjugate of T2 minus infinity less than T1 T2 less than infinity. This is for complex waveform. For example, you may have x of t is say a e power j 2 pi f t. In communication sometimes you will find signals of this type, carriers, right. For such signals, for phasors you may have to consider, it is a complex signal, so therefore you may have to consider the conjugate, right. Similar to the autocorrelation function, we have the covariance function, and the covariance function is given by covariance xx of T1 comma T2, and this is basically you subtract the mean from the waveform x of t, right, at these times T1 and T2, and then basically compute the expectation. So, this is x of T1 minus mu x of T1 times x of T2 minus mu x of T2 conjugate. and it is very straightforward to verify. This is Rxx of T1 comma T2 minus mu x of T1 times mu x conjugate of T2. And these properties in terms of autocorrelation, covariance, etc., will be very useful in many of the tools that we will develop later on in the course. For example, the covariance will be very useful when we have to derive the Kerr-Hunen-Loew transform, KL transform. That means I give you a pool of vectors from from a random process, right? And what can we say if we were to expand this signal in terms of an optimal basis, right, and which is data dependent, which is dependent on the data. And of course, the optimality conditions have to be described more carefully, but we will see this application. Then autocorrelation function. This finds a role when you have to really think about the power spectral density of a process. And why are you interested in power spectral density of a process in communications? Because let us say data is random data. I give you random data which can be zeros and ones in some way, and this random data goes through some filter, right. We assume it is a linear time invariant system, LTI system, so therefore you have a transfer function. The data gets filtered through an LTI system, right, and then we are interested in the power spectrum at the output. That means now this is basically the data is being filtered through this filter, and then we are interested in the spectrum and the channel. For example, why I say about a filter, because the communication channel may be fixed. You cannot control how air is, you cannot control how the magnetic medium is. So the channel is fixed, and if the channel has certain spectral nulls, that means if you imagine the channel has certain holes at some frequencies, right, or I will just say magnitude square. So this is suppose what you have. Then I want to ensure my data, the power in the data is, I do not allocate power in my data which lands up here, right. The channel has a spectral null, which means at frequencies pi by 4, pi by 3, pi by 2 there is 0 energy, right. So even if you pump in power on your data, right, the data also has a spectrum, right. For example, if you think about 1 1 1 1 dot dot dot, it is basically like a DC, right. If you think about data which is 1 minus 1 1 minus 1, basically it is having a high pass component, right. If I think about data which is 1 1 minus 1 minus 1 1 1 minus 1 minus 1 dot dot, I am modulating in some ways. So if I give you random data 1 minus 1 1 minus 1 1 1 1 minus 1 blah blah blah, random data, this has a certain power spectrum if it has certain properties. And often I have to calculate, if I have to calculate the power spectrum, I should calculate the autocorrelation of the sequence. So this is, I give you a discrete sequence here, and for which you have to compute the autocorrelation of this discrete sequence, because you will know the power spectrum from this result from Wiener-Khinchin theorem. And if you know that this has some power at pi by 4 and pi by 3, then when I just multiply this spectrum with this spectrum, basically I am just losing my energy. Though I am having energy in the sequence at frequencies pi by 4 and pi by 3, because the channel has nulls at these frequencies, I am wasting my power by encoding it in certain way. So, this is basically the role of what modulation codes do for us, and how you want to design your modulation codes to choose the spectrum, right. That is the motivation. Keeping that as the motivation, this is important for us to compute autocorrelation functions. So, I said it would be discrete, it would be continuous. So, I gave you an example here where you have these ones and minus ones which are discrete, and you might want to compute autocorrelation of such sequences. Okay. So, let us try to visit an example and then see what how to compute these things. It is not too difficult. So, let us consider a sinusoidal random process. So, suppose x of t is a sine omega naught t plus theta, where theta is uniformly distributed over minus pi to plus pi. Suppose a is also a random variable, possibly distributed according to some distribution, and let a and theta be statistically independent, right. Then if you want to compute the mean of this waveform, so I think I would imagine this picture. There are two random variables a and theta, right, and basically if you think about the sinusoid, you can basically express it in terms of a phasor, right, e power j omega naught t plus theta plus e power minus j by 2j, right. You can express it in this form, and basically what you have is you have two phasors that are summed using this random variable a, and you can think about several such practical scenarios. Imagine I send you a beam of light, right, and then basically this is a, now there is a phase, is a phasor, and then there is basically optical speckle that is happening. Therefore, this a could be a random variable whose length may be distributed according to some distribution, right, and then that is a practical scenario one can think about. So, if a and theta are both random variables and they are statistically independent, and then you have a waveform here for a fixed omega naught is deterministic, right. So, the mean is basically the expectation of a sine omega naught t plus theta, and since a and theta are statistically independent, I could write this as Ea times expectation of sine omega naught t plus theta, right, and this is expectation of a times, I have to average it, right, over the distribution of theta. So, therefore, it is 1 over 2 pi integral minus pi to plus pi sine omega naught t plus theta d theta. Because it is a uniform PDF, I pulled the 1 over 2 pi outside, and we know this is E of A times 0. Because you are just averaging the sinusoid over its cycle, it is 0. So irrespective of what the mean is for A, this is basically 0, right. So it's a sort of an interesting observation for this example. And we can also compute the autocorrelation which is Rxx T1 comma T2 is the expectation x conjugate T1, right. Expectation of T1 times x conjugate T1, which is expected value of A square sin omega naught T1 plus theta times sin omega naught T2 plus theta, which is basically E of A square, expectation of A square times expectation of sin omega naught T1 plus theta times sin omega naught T2 plus theta. Now this quantity here is essentially 1/2 cosine omega naught cosine of omega naught T1 minus T2 minus cosine of 2 theta plus T1 plus T2 into omega naught. You can just verify this from your compound angle formula. Now this has the random parameter theta, this does not have the random parameter theta. This is a constant, expectation of a constant is a constant, this is basically a cosine function, you average it out in that in the interval between minus pi to plus pi, that just cancels out because it is 0, right, the two cycles cancel out. So basically what you will end up is basically E of A square times 1/2 is pulled out cosine omega naught T1 minus T2. That means the autocorrelation depends on the time lag. Okay. So we have gotten basically a sort of a feel for what is a random process. Essentially we have gotten a feel, a sort of an intuitive feel that it is essentially a time function. It is parameterized by two quantities, which is basically zeta and t. So if I fix zeta, it is basically an ordinary time function, and if I fix a t, it becomes a random variable, and then you can do whatever you want to do, basically investigate the statistical properties of this process. You can take a time average, you can take a statistical average, you can take a time autocorrelation, you can take a statistical autocorrelation, right. You can take all the moments, time moments, statistical moments, right. You can do all these kinds of operations, and accordingly there are various notions whether this process is ergodic and so on and so forth. If the time average is equal to the statistical average, it is ergodic in the mean, and it is a very powerful concept. I think a lot of theorems in the foundations of communication theory rest on this notion of ergodicity.